Hello everyone. Today we are going to analyze this beam using slope deflection method. Before analyzing, let us see the slope deflection equations. Consider a random span AB in a continuous beam. In every span, there are two slope deflection equations. For the span AB also, we are having two slope deflection equations for MAB and for MBA. In these slope deflection equations, m of AB is the fixed end moment at A, m of BA is the fixed end moment at B, theta A and theta B are the slopes at A and B respectively. 6EI delta upon L square is the fixed end moment due to sinking of the supports. If in the question nothing is mentioned about sinking or settlement of the supports, we can assume that in the given beam there is no sinking or settlement. In this case, we don't have to consider these two terms. In this question also, nothing is mentioned about sinking of the supports, so we are not going to consider these two terms. We had a little introduction about slope deflection method. Now let us see the beam. In this beam, there are two spans, span AB and span BC. In the span AB, there is a point load 50 kN acting at 2 meter from the point A. In the span BC, there is uniformly distributed load 24 kN per meter acting for the full span. In the point A and in the point C, we are having fixed supports. In the point B, there is a hinged support. Span AB is 5 meter long. Span BC is also 5 meter long. In the slope deflection method, we have to check the number of supports in which slope can occur. Let's see the conditions. In the fixed support, there will be no slope. In the hinged support, there will be slope. In the roller support also, there will be slope. In this beam, in the points A and C, we are having fixed supports. In the fixed supports, there will be no slope. In the point B, we are having a hinged support. In the hinged support, there will be slope. So, the number of supports in which slope can occur is equal to 1. In the point B, we are having the slope theta B. So, in this analysis, we are having only one unknown, that is theta B. If we calculate theta B, we can easily calculate all the moments. Since we are having only one unknown, the number of required equilibrium equations is equal to 1. Now, let's see how to make equilibrium equations. The equilibrium equations can be made at the ends and the joints of the beam. In the joints, summation of the moments will be 0. Using that, we can make an equilibrium equation. Then we have to see the end conditions. In the fixed end, there will be moment, so we cannot make equilibrium equation. In the hinged end, there will be no moment, so we can make equilibrium equation. In the roller supported end also, there will be no moment, so we can make equilibrium equation. Now let's apply those conditions in this beam and make the equilibrium equation. First, let us see in the ends of the beam. We are having the ends A and C. In the ends A and C, we are having fixed supports. In the fixed supports, there will be movement, so we can't make the equilibrium equation. Now let us see the joints. In this beam, there is only one joint, that is joint P. In the joint P, there are two moments, MBA and MBC. We already know that in the joints, the summation of the moments will be 0. That means when we add MBA and MBC, it will be 0. So this is our equilibrium equation. In this analysis, we have to find 4 moments MAB, MBA, MBC and MCB. Also, we have to find 3 reactions RA, RB and RC. Now, let us calculate the fixed end moments. For calculating the fixed end moments, we have to assume every span as a separate fixed beam. First, let us take the span AB and assume that it is a separate fixed beam. Before calculating the fixed end moments, let us see the formulas. In this table, you can see some of the important fixed end moments for the different type of loadings. In the span AB, there is a point load which is not acting on the center. So we have to select this condition. The fixed end moment formulas are minus WAB square upon L square and positive WA square B upon L square. In the span BC, we are having UDL for the full span. So we have to select this condition. The fixed end moment formulas are minus WL square upon 12 and positive WL square upon 12. Now let us apply the formulas and find out the fixed end moments. In the span AB, we are having a point load. This point load is not acting on the center. In this case, we have to split the span into two parts, A and B. We have already seen the fixed end moment formulas minus WAB square upon L square and positive WA square B upon L square. M of AB will be negative because it is acting in the anticlockwise direction. M of BA will be positive because it is acting in the clockwise direction. Let us apply the values inside the formulas. W is 50, A is 2 and B is 3. After calculations, we are getting M of AB is equal to minus 36 kilonewton meter and M of BA is equal to 24 kilonewton meter. Now let us calculate the fixed end moments in the span BC. In the span BC, we are having UDL acting for the full span. We have already seen the fixed end moment formulas minus WL square upon 12 and positive WL square upon 12. Let us apply the values inside the formulas. W is 24, L is 5. After calculations, we are getting M of BC is equal to minus 50 kilonewton meter and M of CB is equal to 50 kilonewton meter. Now let us make the slope deflection equations. First, let's make in the span AB. We have already calculated the fixed end moments. Let us apply them. In the point A, we are having fixed support. In the fixed support, there will be no slope. So let us cut theta A and make it a 0 in both of the equations. The length of the span AB is 5 meter. Let us apply in both of the equations. Finally, in the span AB, we are making two slope deflection equations. Now, let us make the slope deflection equations in the span BC. First, let us apply the fixed end moments. In the point C, we are having a fixed support. We know that in the fixed support, there will be no slope. So, theta C will be 0. Let us cut theta C and make it a 0 in both of the equations. The length of BC is 5 meter. Let us apply in both of the equations. Finally, in the span BC, we have made two slope deflection equations. Now, let us apply the equilibrium equation. In this problem, there is only one unknown, so we need only one equilibrium equation. We already saw the equilibrium equation. The equilibrium equation can be made in the joint B. In the joint B, there are two moments. When we add these two moments, it will be 0. We have already made the slope deflection equations for MBA and MBC. Let us apply them. After the calculations, we are getting A theta B is equal to 16.25. Now let us apply the value of A theta B in the slope deflection equations and find out the final moments. When we apply the value of A theta B in equation 1, we are getting MAB. When we apply the value of A theta B in equation number 2, we are getting MBA. When we apply the value of A theta B in equation number 3, we are getting MBC. When we apply the value of A theta B in the equation number 4, we are getting MCB. So, in this analysis, we have calculated all of the moments. For MAB, we got a negative value because MAB is acting in the anticlockwise direction. For MBA, we got a positive value because MBA is acting in the clockwise direction. For MBC, we got a negative value. That means it is acting in the anticlockwise direction. Finally, for MCB, we got a positive value. That means it is acting in the clockwise direction. Now, let us calculate the reactions. First, let us take the span AB and calculate the reactions. In the span AB, there are two moments, MAB, which is acting in the anticlockwise direction, and MBA, which is acting in the clockwise direction. In the span AB, first I am going to find RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. The vertical reaction RA is acting towards the point B in the clockwise direction, so it will be positive and the distance is 5. So 5 RA. The point load 50 kN is acting towards the point B in the anticlockwise direction, so it will be negative and the distance is 3 meter. So minus 50 into 3. Then there are two moments. The moment 29.5 is acting in the anticlockwise direction, so it will be negative. The moment 37 is acting in the clockwise direction, so it will be positive. After the calculations, we are getting RA is equal to 28.5 kN. To calculate RB1, let us apply the rule summation of vertical forces is equal to 0. In this span, there are three vertical forces RA, RB1 and the point load 50 kN. The reactions RA and RB1 are acting upwards, so both of them will be positive. 50 kN is acting downwards, so it will be negative. We have already calculated RA 28.5, so instead of RA, let us apply 28.5. In this way, we can calculate RB1, which is equal to 21.5 kN. Now, let us take the span BC and calculate the reactions. In the span BC, there are two moments, MBC, which is acting in the anticlockwise direction, and MCB, which is acting in the clockwise direction. In this span, first I am going to calculate RB2. For that, I am going to take moment about C. the vertical reaction RB2 is acting towards the point C in the clockwise direction, so it will be positive and the distance is 5, so 5 RB2. The UDL 24 kN per meter is acting towards the point C in the anticlockwise direction, so it will be negative. When the UDL comes, we have to multiply with the distance and a distance upon 2. Here the distance is 5 meter, so 5 into 5 upon 2. Then there are two moments. The moment 37 is acting in the anticlockwise direction, so it will be negative, and the moment 56.5 is acting in the clockwise direction, so it will be positive. After the calculations, we are getting RB2 is equal to 56.1 kilonewton. Now let us apply the rule summation of vertical forces is equal to 0. In this span, there are three forces RB2, RC, and the UDL 24 kN per meter. RB2 and RC are acting in the upward direction, so both of them will be positive. The UDL is acting downwards, so it will be negative. For the UDL, we have to multiply with the distance to get the total load. We have already calculated RB2. Let us apply the value. In this way, we are getting RC is equal to 63.9 kilonewton. We have calculated the reaction in the point B 2 times. Let us add both of the values RB1 and RB2. After adding, we are getting RB, which is equal to 77.6 kilonewton. Now we are going to draw the shear force diagram. Before drawing, let us find the shear force values. I am going to calculate the shear force values from the point A and towards the point C. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. You can see the calculations here. Using the values, we can draw the shear force diagram. Now we are going to draw the bending moment diagram. Before drawing the bending moment diagram, we have to make the free moment diagram and then the end moment diagram. Finally, we have to combine the free moment diagram and the end moment diagram to get the bending moment diagram. To draw the free moment diagram, we have to consider every span as a separate simply supported beam. First, let's see the span AB. In the span AB, there is a point load 50 kN. This point load is not acting on the center. If the point load is not acting on the center, the formula for the maximum bending moment in a simply supported beam is WAB upon L. Here, W is 50, A is 2, B is 3, and L is 5. After applying the values inside the formula, we are getting 60 kN meter. If UDL is acting for the full span in a simply supported beam, the formula for the maximum bending moment in the center is WL square upon 8. Here W is 24, L is 5. Finally, we are getting 75 kN meter. We know that when the point load comes, the diagram will be in a triangular shape. When the UDL is acting, the diagram will be in a parabolic shape. Now let us see how to draw the end moment diagram. Using the end moments, we have to draw the end moment diagram. First, we have to draw this line. We have to draw these clockwise and anti-clockwise curves according to the moments. Then we have to see the direction of the arrows. All of the arrows indicate upwards. So all of the points come above the line. Even though in the joint B we are having two movements, we have to make only one point because both of these arrows are indicating upwards. That means we will have only one point. End moment diagram will be negative if it comes above this line. It will be positive if it comes below this line. Right now, all of the points are coming above the line, so it is negative. Now, let us combine the free movement diagram and end moment diagram. You can see that I have combined both of the diagrams. Wherever they are acting alone without mingling with one another, we have to mark the values with the sign. Here the end moment diagram is coming alone. Here the free movement diagram, then end moment diagram, then free movement diagram, finally the end moment diagram. Wherever they are together, we are not marking anything. We just keep the space empty. Now we are going to end this session. Thank you for watching this video.